For decades, humanity has pushed the boundaries of how fast we can travel through the air. We conquered the sound barrier, and now a new frontier beckons hypersonic flight. This term describes moving at speeds greater than Mach 5, or 5 times the speed of sound. At these incredible velocities, the world starts to shrink. A journey that currently takes a full day of flying could be reduced to just a couple of hours. Brisbane-based Hypersonix Launch Systems is one of the pioneering companies turning this science fiction concept into a tangible reality. They are developing aircraft designed to fly at speeds up to Mach 12, a speed that could revolutionize global transport, defense, and even access to space. Flying at 12 times the speed of sound is special for reasons that go far beyond just saving time on a long-haul flight. At approximately 14,820 kilometers per hour, an aircraft becomes exceptionally difficult to track, intercept, or defend against, making it a game-changer for military and surveillance applications. It opens up a new realm of responsiveness, where assets or information can be deployed anywhere on the globe with unprecedented speed. For scientists, this speed offers a unique platform for research in the upper atmosphere. For commercial travel, it represents the next great leap forward, promising a future where continents are connected like neighboring cities, forever changing our perception of distance. This incredible ambition is taking a major step forward as we speak. As of November 2025, Hypersonix has successfully secured an impressive $46 million in funding from international investors, including a significant investment from Australia's National Reconstruction Fund Corporation. This financial backing is a powerful vote of confidence in their vision and technology. It provides the necessary resources to accelerate the development of their groundbreaking aircraft, expand their advanced manufacturing facilities in Queensland, and establish a stronger presence in the United States. This momentum is crucial as the company prepares for its first major flight tests, moving from computer models to real-world performance. The pursuit of hypersonic speed is not just a commercial or scientific endeavor, it has captured the attention of defense organizations worldwide. The United States Department of Defense, through its Defense Innovation Unit, has selected Hypersonix for its HiCat program. This initiative seeks to develop reusable and high-cadence hypersonic test aircraft, shifting the paradigm from single-use missiles to versatile, aircraft-like platforms. Being the first company chosen from a pool of over 60 applicants underscores the uniqueness and potential of the Australian firm's approach. This collaboration places Hypersonix at the very heart of Western efforts to master this transformative and strategically vital technology. At the core of Hypersonix's revolutionary aircraft is its proprietary engine, named SPARTAN. This is not a conventional jet engine with spinning turbines and complex machinery. The SPARTAN is a scramjet, a supersonic combustion ramjet, which is an air-breathing engine designed to operate efficiently at hypersonic speeds. What makes it truly unique is its design philosophy. It has absolutely no moving parts. This elegant simplicity makes it more robust, easier to maintain, and theoretically far more reliable than traditional engines, especially under the extreme conditions of hypersonic flight. This design significantly reduces the risk of mechanical failure, a critical factor when traveling at over 14,000 kilometers per hour. The innovation doesn't stop with its mechanical design. The SPARTAN engine is manufactured using advanced three-dimensional printing techniques, also known as additive manufacturing. This method allows engineers to create incredibly complex internal geometries that would be impossible to produce with traditional casting or machining. These intricate shapes are essential for managing the airflow and fuel mixing inside the engine at hypersonic speeds. Furthermore, three-dimensional printing enables the use of specialized high-temperature alloys and composite materials that can withstand the immense heat generated during flight. This modern manufacturing approach also speeds up prototyping and production, allowing for rapid iteration and improvement of the engine's design. Perhaps the most forward-thinking aspect of the SPARTAN engine is its fuel source, hydrogen. While most hypersonic programs around the world rely on kerosene-based jet fuels, Hypersonix has committed to using clean hydrogen. When green hydrogen, which is produced using renewable energy, is used as fuel, the only exhaust produced by the SPARTAN engine is pure water vapor. This means the aircraft generates zero carbon dioxide emissions, offering a pathway to sustainable, high-speed flight. This commitment to environmental responsibility sets Hypersonix apart, positioning its technology not just as fast, but also as a potential solution for the future of clean aviation. The choice of hydrogen as a fuel is also a strategic one from a performance perspective. Hydrogen has a much higher energy content per unit of mass compared to traditional hydrocarbon fuels. This means that less fuel weight is needed to achieve the same amount of thrust, which is a critical advantage in aerospace engineering, where every gram matters. The hydrogen also serves a dual purpose. Before being injected into the combustion chamber, the cryogenically stored liquid hydrogen can be circulated through the engine and airframe to absorb the intense aerodynamic heat, acting as a regenerative cooling system. This clever synergy helps solve one of the biggest challenges of hypersonic flight while powering the aircraft. Hypersonix is bringing its technology to life through a series of progressively advanced aircraft. The first of these to take to the skies is the DART AE. This is an 11.5-foot long, uncrewed demonstrator vehicle powered by a single SPARTAN engine. The DART AE is not designed for a specific mission, but serves as a crucial flying testbed. Its purpose is to prove that the three-dimensional printed, hydrogen-fueled scramjet engine works as designed in a real-world flight environment. It will gather invaluable data on aerodynamic performance, engine efficiency, and material science at hypersonic speeds, validating the computer simulations and wind tunnel tests conducted on the ground. The upcoming flight test of the DART AE is a highly anticipated event in the aerospace community. Scheduled for late 2025, the launch will be conducted from NASA's Wallops Flight Facility in Virginia. The demonstrator will be carried to its test altitude and speed by a Rocket Lab HAST booster rocket. Once released, the SPARTAN engine will ignite, aiming to achieve the world's first sustained hypersonic flight powered by green hydrogen. This flight, conducted under the watchful eye of the US Department of Defense's HyCat program, represents the culmination of years of research and development and is a critical milestone on the path to operational hypersonic aircraft. Building on the lessons learned from the DART AE, Hypersonix is also developing a larger, more capable platform called VISR. This 8-meter-long aircraft is envisioned as a fully reusable vehicle designed for intelligence, surveillance, and reconnaissance missions. Powered by 4 SPARTAN engines, the VISR will be constructed from advanced ceramic matrix composites to withstand the extreme heat of sustained flight between Mach 5 and Mach 10. Its reusability and rapid turnaround capability would give defense forces an unprecedented ability to monitor vast areas with a platform that is almost impossible to counter, treating the hypersonic realm as a space for aircraft, not just expendable missiles. Beyond the VISR, the company has even grander ambitions with concepts like the Delta Velos. This next-generation vehicle is being designed as a reusable launch system that could deliver small satellites into low Earth orbit. By flying to the edge of the atmosphere at Mach 12 before releasing its payload, it could dramatically reduce the cost and environmental impact of accessing space. This air-breathing first-stage approach avoids the need for massive, expendable first-stage rockets, making space launches more like a routine airline operation. These platforms, from the DART AE testbed to the Delta Velos launcher, showcase a clear and ambitious roadmap for the future of hypersonic technology. While the promise of clean hypersonic flight is inspiring, the engineering challenges are immense. One of the most significant hurdles is managing the extreme heat generated by air friction at speeds above Mach 5. The leading edges of an aircraft can reach temperatures hot enough to melt steel, requiring the use of exotic and expensive materials, like ceramic matrix composites and nickel-based superalloys. Hypersonix is tackling this by designing its aircraft with these advanced materials. and by cleverly using its liquid hydrogen fuel as a coolant, circulating it through the airframe before it is fed into the engine, a process known as regenerative cooling. Another major technical challenge lies in storing the hydrogen fuel itself. To be dense enough for practical use in an aircraft, hydrogen must be kept as a liquid at extremely cold temperatures, around -250 degrees Celsius. This requires heavily insulated cryogenic fuel tanks, which are bulky and complex. Preventing the fuel from boiling off due to the intense heat seeping in from the aircraft's skin is a constant battle. Engineers must develop lightweight yet highly effective insulation systems and tank structures that can withstand both the cryogenic cold inside and the searing heat outside, all while being strong enough to handle the stresses of flight. Building components that are strong enough to survive the violent forces of hypersonic flight is another key difficulty. The combination of intense vibrations, extreme thermal variations, and tremendous aerodynamic pressure can push materials to their absolute limits. Every part, from the engine structure to the control surfaces and the fuel lines, must be meticulously designed and tested to ensure it can perform flawlessly in this punishing environment. This is where Hypersonix's use of three-dimensional printing offers a distinct advantage, allowing for the creation of unified, stronger parts with fewer joints and weak points compared to traditional manufacturing methods. Should Hypersonix and other pioneers in this field successfully overcome these challenges, the impact on our world could be profound. A future with operational hypersonic jets would mean that a business meeting in Sydney could be attended by someone from London on the same day. Urgent cargo, such as medical supplies or disaster relief equipment, could be delivered across the globe in under an hour. It would usher in an era of unprecedented global connectivity, shrinking our planet and potentially fostering greater international collaboration. The journey is long and fraught with difficulty, but the successful flight of vehicles like the Dart AE could be the first step toward making that connected high-speed future a reality.